All right, I'm resuming, and I I apologize. As I predicted, I forgot to start the recording at the beginning of today's lecture. So if you guys notice that I don't have recording going on, obviously, if you're here, you're not as concerned, but I would appreciate a reminder to turn on recording. I'm just laser focused on everything else. At any rate, I apologize for the recording skipping the first part of the today's lecture. And now here's part two. So we'll resume screen share, and we'll talk a little more about some of the uh, other aspects of C programming. So this is based on, these two fellows in ancient times actually created the C programming language at the Bell Labs, and there was some language called B, and they decided theirs was going to be called C, and so that's why it's called C. But they wrote a book called the Kernighan and Ritchie book, and it's still in print and still widely used and famous. I don't use this book anymore. Sorry, it's really old. Okay. I haven't looked at it in many years. So let's talk about constants in C. And by constants, we mean, like I typed in the number pi, 3.14159, in that example before. And that's a constant. But I might have an integer constant or a string constant. And in C, there's a big focus. C was kind of like a step away from assembly language, and assembly language is used or traditionally was very bit level oriented. And so C still retains the ability to go down to bit level when you need to, and we will need to. And so we can do really precise things with memory. So first, let's review binary, hex, and octal. You should know this. You should also be able to find easily online resources to refresh your memory. But binary, of course, represents numbers as either 0 or 1 and nothing else. So here is a table where we're counting up in binary, 0, 1, 2, skipping some, 7, 8, and so forth. And as you know, each of these positions represents a power of 2. 2 to the 0 is 1. 2 to the 2 is 2. 2 to the 1 is 2. This is position 0. Position 1 is 2. If you have a 1 here, like 100 binary, that's 4, etc. And you add all the positions that have a 1 in them. So this would be 4 plus 2 plus 1. 4 plus 2 plus 1 is 7. And hex and octal are the same from 0 to 7. And they change when we get to 8 because it basically boils down to just, I'm not going to mess with that. Okay, it boils down to grouping the bits into groups and encoding them so that we don't have to write a 64-bit string of ones and zeros, which would just be impossible, or even a 16-bit one is pretty hard. So what we do in hex is we group the bits into groups of 4. I've only shown one group of 4 here, and we encode them up to the number 9. We just encode them as their decimal equivalent. But when we get to 1010, there is no single digit decimal number because this has the value 10. It has 8 plus not 4 plus 2 plus not 1. So it's 8 plus 2 equals 10. And so we call that A, capital A usually. And the next one after A is obviously B, until we get to this last one. This is the last possible 4-bit code or cluster group, and it's all ones, and that's F. And then after that, it would carry to the next position. So we can encode a longer number by just grouping it into these blocks of 4 and converting it according to this table. It means that you have to memorize things like B is equal to 1011, which is not so obvious. Now, what's octal? Octal is you group them into groups of 3 bits. So all of these are the same until you get to 7, which is the last possible 3-bit grouping. And then what you do is you go to the next digit. So this is the next octal digit, which is a 1 in the second group of 3. And the first group of 3 has the value 0. The first group of 3 here has the value 1. So this is 1, 1 in octal. For some reason, octal is not nearly as popular anymore. It used to be used more often, like when I was an undergrad, which is very long time ago. But I like it because you don't have to memorize anything. You just convert and you get what you want, as long as you group these into groups of 3. But in the PC world, the hex is very, very universal. And so pretty soon you'll have this down and memorized anyway. Or maybe it doesn't matter, but you'll see a lot of hex numbers. If you see numbers composed of 0 through 9 plus A through F, that's a hex number. Okay, so this is sort of a big example of the hex number D2FB. Okay, so there's a D, a 2, an F, and a B. And this B is, this is supposed to be an example where we fill it out ourselves, okay? So B is 1011, and we put that in here. This would be, to convert it to decimal, we have to take the value, B is 11 times 1, so that we'd put an 11 here. And this is 16 times F, which is 15. So we put 16 times 15 here, etc. All right. Now, let's say we write the number 25 in C. That's going to be interpreted as, or compiled is more appropriate, as decimal. So it's just regular 25. There's 25 students in the class. If you want to use a hex value in C, you prefix it with 0x. So 0x2f is the hex integer, which is 15 plus 2 times 16. 32 plus 15, 47, okay? And octal values are have a leading 0, no x, just 0 to 8. That's a little tricky, you might not know that, but C will interpret that as octal. And this is actually an error. What's wrong with that? Anybody know what's wrong with this octal constant?
There's no 8.
Precisely. This is illegal because octal digits only go up to 7. And so the C compiler would reject this. Said, I can't understand an octal constant that has an 8 in it. Okay. So now here is something where we're going to talk, change gears a little bit. We're going to talk about how to write professional C code as opposed to C code which compiles correctly, okay? So it's very possible to write 50 pages of C that work, that do the job correctly and perform well, but is bad code. And it's bad if it's not human readable. And there's many cases of organizations where they trusted one programmer to implement some very critical, mission critical code. And that programmer did it, and that's fine until the person left. And then that person left and their code was unmaintainable because nobody understood how it worked, nobody could read it, and nobody could fix problems with it or expand it or update it. This is very, very critical. So in professional companies like Google, you have to follow all kinds of standards in your code, like we have in a simplified form in this course. And your code has to follow a whole bunch of standards to make it readable. So it's uniform. So in a way, if you read some code at Google, you don't even know who wrote it because it follows the coding standard of Google. And they won't accept your code into production until experts have reviewed it and it's passed a checker for these rules. Okay, so one of the big things we're going to talk about here is symbolic constants using the pound define directive that we talked about already, instead of typing numbers into your code. So like I just did it, right? So I gave you an example, which I can actually bring back up somewhere. Yeah. So I said, well, there's 5 suffixes and I'm going to do this 15 times. So I put numbers into the code, or all these numbers. And that's fine in this little thing. It's very simple. Everybody can understand it. But that's terrible to do in professional code. And even at the scale of your guys' lab projects, you will get the benefit of not doing this. So what do we do instead? Okay, so it will be readable and it'll be easier to change. So here's some examples. So pound define example constant D 1, 2, 3, 4. Okay, that's decimal. This is just explaining decimal and octal again, and H and O, decimal, hex, and octal. And now we have integer x equals example constant D. It means x equals 1, 2, 3, 4. All right, etc. And so actually, this is a good exercise here. So we've got those examples, example constants, and we've assigned x, y, and z to those values. So this is kind of more going back to hex and decimal conversion. Which of these statements print? So why doesn't everybody just take a minute to think about that, and then maybe we'll try this code, see what happens. Does everybody understand what we're doing now? Anybody not understand? Want a clarification?
Professor, can we scroll up again to see the value of x, y, z? Yep. Thank you.
Also, these slides are on Canvas right now. Maybe I can do a little more magnification. That's better, huh? A little less magnification. All right, so basically, I'm going to sort of jump in. Basically, you probably figured out that what this boils down to is figuring out the, say, the decimal value of example constant h and example constant o, and then you can evaluate whether these equals statements are true or not. So we're not sure if 4d2 is equal to 1, 2, 3, 4. And to be honest, I can't even remember, even though I created these examples. So let's go into code blocks again and see what happens. I'm just going to, by the way, I'm going to comment out this, the earlier example. And in C, we have the ability to define multi-line comments with slash star and star slash. So now we have a whole new program in main, and we're defining these pound defines, and we're then setting up some ints, and we're going to print some and see what happened, or we're going to see if these print. So hello there, what's up, Doc? The rain in Spain falls mainly on the plains, which is a corny song from the 60s. And we're going to, oh, I have to X out of some bug, and we have to compile it. Warning, on line 32, because I have a typo there. This is a classic C programming typo, which is using 1 equal instead of 2. And again, the warning helped me out. What I meant is to not to assign a new value to Z if this is true. So thank you again, warning system. And that compiles, and we'll run it. And so what printed is hello there and what's up, Doc, the first two, but the last two are not true. The last two are false. Does that make sense? So why is it false? Because Z is example constant O, which is 2332. But the reason is that this is a decimal value, not a constant, not a hex value, not an octal value. So if I put a 0 there, it's now an octal interpretation. We'll save it. And now the rain in Spain will print, but mainly falls on the plains will not print. And that's also true. Okay. So let me see if my slides have a typo. I may have done this on purpose to teach people about this bug. I can't remember, because it's so easy to miss that. Very experienced people still do it. And what this says is Z is equal to the decimal value 2322, not, and it will evaluate to true because it's a non-zero value. So this will print if you just leave the single 0 there. Actually, let's verify that. The single equal there. All right, so I'm going to do this one. In fact, let's make some random wild number, 93625. Okay, none of the above. And it's warning me because this is such a common bug. And in fact, falls mainly on the plains did print, even though Z is not equal to this number. But now, after this is actually an assignment statement, which is just like this one, and changes the value of Z. In C, if the predicate or the thing inside your parentheses on an if statement, if it's not 0, the if statement considers it true. And so that's why this actually prints. Questions? Okay. Now that is really kind of flashing back to octal, hex, and decimal conversion, but we're going to talk more about this issue of making your code readable and why these pound defines are really, really valuable. So let's say that you have to control a CD-ROM drive. That's kind of an old thing. You remember that from when you were kids, maybe. And you want to open and close the door. So there's a bit in the hardware that opens and closes the drawer. And let's say it's the 4th bit in a register that's located at this hex address. And we'll talk more about this a lot, but basically registers are little slots that hold bits in the hardware, and they can be, and most commonly are mapped into the same address space as memory. So they're not memory, well, they kind of are memory because they store a bit, but they're also wired to hardware. So there's a bit in that register. So so let's say that there's some function IO register set, the address and the value. And address is this address here, and value is the bit pattern you want to put there. In this case, we want to set the 4th bit. So technically, you could write this IO register set OX2DA OX10 in hex of actually the, yeah, so this digit encodes bits 0, 1, 2, and 3. And so this is actually the 4th bit. And that's what we want to set. Okay, fine. But this code is not human readable. It's a bunch of numbers. You have to really know what's going on to know what these numbers mean. And it's a waste of your brain to memorize that stuff. So what we're going to do is write our code to be more readable. We're going to make a long symbol, CD-ROM control register, and we're going to pound define that to the hex constant. And then we're going to make another symbol for the command, which is very understandable. And we're going to pound define that to this bit. And now further way down inside some complex code, we're going to write the code IO register set CD-ROM control register CD-ROM door open. So this is much more understandable by humans. And that means it's more maintainable. And you may have dozens of these instructions throughout a complicated, say, hardware driver. But then manufacturing calls you up and says, oh, we've got a new design because we can save $20 or more like 20 cents. We can save 20 cents on the CD-ROM if we move the control register to 2DF instead of 2DA. So you go and you change it right here and all your code is instantly correct and still readable and understandable. That's a huge benefit. Even in 474 lab code, you will get paid off for a payoff for that. And so we're going to enforce this. And if your code has numerical constants in it, like I did in the first thing, you will get dinged if you don't do stuff like this. Questions? Okay, so now we're going to talk about manipulating bits directly. And also doing logic in an if statement. So you're probably familiar with combining two tests in an if statement using something like and. If this is true and that is true, then do something. But we're going to use, we have those in C, but we have kind of two completely different flavors that do different things. So logical operators are we can use the expression true, capital T, false. False is actually just the same thing as a 0 integer, but this is much more readable code. And then if you want, you know, to do a logical and, you use 2 ampersands like that, A and B. If A is true and B is true, then this expression's true. Vertical bars for or, that's on your keyboard on the right-hand side. And exclamation point for not. In Python, for example, it's a tilde, but in C, it's an exclamation point. And that's straightforward to use in, say, an if statement. But we have a lower level and very powerful feature called bitwise operators in C. And so now suppose we have these kinds of types, and we'll talk more about what they mean, but int is integer. And how many bits is an integer? Well, it turns out that depends on what machine you are compiling your code for. And so a big machine like your laptop, big, an Intel 64-bit Intel or AMD type chip, it's going to be 64 bits, which is a lot. For the Arduino, it's going to be 16 bits, which presents some interesting challenges because it means you can only represent a number up to 65536, or it's actually 65535, if it's not signed, if it's only positive numbers. If it's positive or negative, you only can go up to plus 32768 and minus 32768. Okay, so but let's focus for now on 16-bit integers. So it's like a strip of 16 ones and zeros. That's kind of the unit inside the memory for ints. And now we can do things with those bits using 1 ampersand instead of 2, 1 vertical bar instead of 2, and we get some other cool symbols, which we'll go into. So now let's define some constants for various bits. So bit 0 is this in hex. Bit 1, 2, 3, 4, bit 5, and bit 6. So, okay, that's our bits in position order from the least significant bit 0 to a more significant one, bit 6. And let's make some constants. So here's one, x equals hex 0b. So the last 8 bits of that, which is all I'm going to bother with here, are the first digit, the most significant hex digit is 0, which is indicated by these 4 bits. And the least significant 4 bits is this one, which has the code B. And now here's another one, which is octal 11. And in memory, that's going to have a 1 in the second 3-bit group and another 1 in the first 3-bit group. Going from right to left, this is least significant bit, and this out here is the most significant bit. And by the way, that can depend on your machine architecture. So that's called the endianness of the machine architecture. So there are machine architectures where on the right side, it's the most significant bit. We're going to stick with this and not be confused. All right. So now here's a cool feature, which is called shifting. So this means shift the bits left and right. And shift by 2 means shift it 2 positions. So x was this originally. This is the original value of x. When we shift it to the left by 2 positions, we get this. And if you take a look at, I just want to draw. Okay, let's review, pen. All right, so this bit goes to here. This bit goes to here. This bit goes to here. And this bit goes to here because we've shifted left by 2 positions. I hate having to grab this thing every time. I still am looking for a good annotation solution. Okay, does that make sense? Everything's shifted over. Now we're going to do Y, which is this one that I've scratched out now. I wonder if I can clear those. Forget it. We'll just leave them there. So Y is 1001 in binary, 11 in octal. And now what we're going to do is do the bitwise AND between Y and bit 3. So bit 3 is just the third, there's a 1 in the third position, which just looks like 1 0 0 0, 3 zeros and a 1. And we're going to AND that with Y. So that means this one will be 0 because it's a 0 ANDed with 1, 0 0 0 0, and this one will be 1 1. So that's why when we AND them together, we just get 1 here and we do not get the 1 here. Does that make sense? Bit 3 is this position right here. It's a binary number which has a 1 in that position, is another way to say it. Okay, now we're going to say, let's take Z, which is this number, that's the result of the shift, and we're going to OR it with bit 4. So bit 4 is just another shift from bit 3. So it's this position. And so what we're going to do is we're going to take this binary and we're going to OR it with a 1 in this position. And that fills in this 0 and keeps these because it's logical OR. And that's what we have. So that's what bitwise logical operations are, including shift, AND, and OR. Any questions about that?
Hi, Professor. I have a question.
Okay.
Can we specify whether to make arithmetic or logic right shift?
I'm sorry, say that again.
Can we like make the decision to do whether arithmetic right shift or logical right shift?
I'm not sure what your question means in this context. I'm just teaching you about the bitwise right shift or left shift. Now, what I think you might be asking about is that if you know about binary numbers, which I'm sure you do, you realize that if I shift something to the left 1 position, that's like multiplying the number by 2. And if I shift it 2 positions, that multiplies the number by 4. Just like in decimal, if I have the number 16 and I shift it 1 digit over, then I have 160. I multiply it by 10. So if we shift binary, we multiply by 2. And if we shift to the right, we divide by 2. Is that what you're talking about?
Yeah.
Right. So generally, yeah, if you do an integer divide and you write a statement like, well, let's just say, suppose we had the statement int z equals x times 4, okay? Is that equivalent to this left shift? And I think so. There might be subtle differences in how internal bits are set inside the CPU, okay? We're not going to go into that, but there are a bunch of bits called status bits that are set after every operation. For example, if you try to divide by 0, it will set a bit called divide by 0 and not return a value. Or if there's a sign bit, if you get a negative result from an operation, the sign bit will be set. And so there's a whole, it turns out there's like 4 or 5 bits like that are set as a result of specific machine instructions. If I do a left shift, let's say I do a right shift by 2 compared to a divide by 4, the data in the int is probably going to be the same, but there may be different side effects on those bits. So I'm not going to say they're totally equivalent, but they are very similar. Does that answer your question?
Yes. Thank you.
Great. Good question. Others? All right, so this bit manipulation is probably new compared to what you've done in previous programming, but it's a powerful feature because we will be caring about specific bits sometimes. So I think I'm going to leave these exercises to you guys to do offline. And, you know, when I first did this, maybe your calculator had this function, maybe it didn't. But you can find about 200 websites to do this for you in about 2 seconds of Googling. So that's fine. Go ahead and use that. I don't care. I don't need you to be a mental conversion whiz on these. I want you to understand them, but I don't need you to be able to do that really fast mentally. But I recommend that you do these to understand the concepts. And I can, if anyone is interested, I'll put out the answers to these. Or you can just write your own little C code in code blocks to implement these and then see what happens. You could write a function that prints out a binary number. Now, interestingly, printf, we talked about printf, and it has all these format codes for including hex and octal and decimal and strings and floating point, but it does not have a binary output format code. And so you have to write one yourself using bitwise operators to check each bit and shift and print out a 1 or a 0. And when you're done, print a new line or something. It's a fun little exercise. I assigned it one time, but not this year. Okay. All right, let's talk about integers. Very common, very important, especially in these in Arduino and so forth. They're often, you think of it as a 16-bit binary number, and but we'd like to represent negative numbers too. And so how do we do that? We obviously need to use a bit to represent whether the number is negative or positive, but they do it in not quite a straightforward way. So there is a type called unsigned int, which we can declare by just using unsigned int instead of int. And then we don't have any signed bits. We can't represent negative numbers, but we get this range all the way out to 2 to the 16th minus 1, including 0, which gives you 2 to the 16th values to have. So that's good. A lot of times, you know, you're counting milliseconds or something, and wow, you realize, oh, I'm counting milliseconds in a real-time embedded system, and I only can represent 6.5 seconds. So you have to think about this. There's ways around it. Okay. So here's some unsigned characters, integers, and also long ints. So you can tell it, well, 16 bits isn't enough for what I want to do. So please give me what's called a long int. And you can't tell it, I want 32 bits, but on a particular machine architecture, because C can be compiled on all these different chips and CPUs, you will have a standard length for long, which will be typically twice as long as the standard length for int. So maybe on a Pentium, this would be 32 and 64, or even 64 and 128. I can't remember. Not a Pentium, but a Core i9 or whatever. All right, we're almost done for the day. Let's try to get through a little more. Yeah, so I recommend writing a function to print a binary value of a 16-bit word. I'll show it to you quickly, but you guys should try to do this. Here's a function called bin display. Its argument is an unsigned integer named x, and we declare two more internally, I and j. And then we go through the 16 bits with a for loop, and we shift the value 1. We take a 1 sitting there in the least significant bit. It's the same in hex, octal, and decimal. It's just 1. And we shift it to the left by this many positions. So each time I is incremented, we shift it further. We want to print them starting from the most significant digit, not starting from the least significant digit, because then it would print out backwards, right? So that's why it's 15 minus I here. And then we test that bit. If this bit j is set in the value x, we'll print a 1. But if it's not, we'll print a 0. And we'll do that 16 times, and we get the binary value. So I'm going to deliberately not send you that file yet, because you guys should try it in code blocks. Okay, and I'm going to make this the final topic for today in the last few minutes. 2's complement. So this is how we represent negative numbers. And you would think, well, you take 15 bits for the number magnitude and 1 bit for the sign, and you're done, right? It turns out that back in the day, the math portion of the CPU was complex and expensive. And if you use this different representation, which is not quite that simple, then mathematical operations like addition and subtraction become easier. And so that's why we're going to learn about 2's complement. Today, I think it wouldn't matter. It might increase the surface area of your CPU chip by a tiny, tiny fraction to do it the logical way. Okay, so how to convert a number to or from 2's complement. So you complement all the bits. Complement means if it's a 1, you make it a 0. If it's a 0, you make it a 1. And then you add 1 to it. You increment it. And in 2's complement notation, this is equivalent to negating the number. It's equivalent to multiplication by minus 1. So that lets us get this range of numbers from, we don't get n bits anymore, we get n minus 1 bits, but we can go from minus 2 to the n minus 1 all the way to plus 2 to the n minus 1 minus 1. Okay. So let's see how that would look. Let's negate assigned 2's complement integer using bitwise logical operators and addition. In other words, instead of just saying x equals minus y, which we could do, we're going to do it the hard way to simulate this notation or reproduce it. Do not just multiply by minus 1. So, okay, so we're going to make a 2's complement demo. We're going to say, well, a is minus 23. And by the way, when you say this, it means 2's complement at the binary level. And we have an int b and I and j. These are not initialized yet. Both of these forms of variable declaration are A required, or one of them is required, and B, both are acceptable. So you don't have to initialize. Typically, the compiler will initialize it to 0 for you if you don't say int b equals 0, but it's, if you need that, it's better practice to explicitly do that. And now we're going to say, well, the decimal is a, and the binary is something. And then we're going to say b equals a, and then we're going to whoops. I don't know why we did it this way, but then we're going to do, oh, I see. Then we're going to binary display the value of a. So this is converting it from an int to an unsigned int, which is required by that routine we did to display the bits. And then we're going to print the complement. And this is the bitwise logical operation to flip every bit in the word A. So now we have a different thing. We don't just have a negative number. We have the complement. And now we're displaying those bits again. And then we're saying, okay, here's the complement plus 1. So this thing is just making it print on a new line. And now we're saying 1 plus the complement of A. And we're displaying that in binary as well. And now we're going to compare this new value with A. And these should be the same, because this should have negated B, if that makes sense. Probably doesn't. So I'm going to actually see if I can't paste this into code blocks and run it in the remaining couple minutes. Why didn't that comment everything? Oh, because there's already multi-line comments. Okay, everything's gone. Paste. Let me copy this again. Actually, I have the output there, so I probably don't need to, but it's fun. Okay, here it all is. And we have, this is our function prototype. This is main. And now we'll run that program. Let's see if it compiles. Okay, I'm going to leave that and skip it. Let's instead just show you this test output. So the way that works is up here, we printed out A right in this position here. And we get minus 23 as we expect. This is the binary value for minus 23 in 2's complement notation. And as a rule of thumb for smaller numbers, you see a lot of ones on negative numbers in the most significant bits in 2's complement, because that's just how it works. The complement of 23 is, or the complement of minus 23 is this. I've flipped every bit. And now I take 1 plus the complement and I get this. And this should be 23 because I started with minus 23. This is minus 23, and I'm reproducing the act of negation in 2's complement. And now I print them out and they match. So that is a little bit complicated, but it's really some extremely simple operations to negate a number. Complement the bits and add 1. That's the takeaway. So thanks. I will see you guys Monday. I have some, I guess I have no sign-up slots this week, but the full deck of sign-up slots opens up next week, including on Monday. So if you need those. Otherwise, I am going to be on Piazza as I have been already. And so throw your questions and issues on there for me and the TAs to deal with. The TA office hours are up. They're great TAs, and look forward to the rest of the quarter with you.